There's a current running through the middle of the Pacific Ocean that has quietly rewritten America's weather 3 separate times in the last 12 years. It doesn't make headlines when it starts. It doesn't get a name on the evening news the way a hurricane does, but by the time it's finished, it has decided who gets the drought, who gets the flood, who gets the mild winter, and who gets the one that breaks pipes across 3 states. And for the first time in years, it is starting to move again. I'm not talking about a single storm system. I'm not talking about one bad forecast for one bad week. I'm talking about the ocean itself shifting gears thousands of miles from anyone's backyard in a way that eventually reaches every single one of us. Here's the part that changes everything. This shift doesn't stay in the ocean. It reroutes the jet stream. And the jet stream is the thing that decides for the entire country at the same time where the rain goes and where it doesn't. I'm not telling you a specific disaster is guaranteed on a specific day. I'm telling you the ingredients for a nationwide pattern shift are already lining up, and almost nobody outside a handful of climate scientists is watching it closely enough to explain what it actually means for the place you live. Stick around, because by the end of this, you're going to understand a piece of the atmosphere that quietly controls more of your life than the local 10-day forecast ever will. This is the story of El Niño and La Niña, and the rare kind of transition happening between them right now, one that climate scientists have started describing not as a normal seasonal shift, but as a full pattern reset for the entire United States. And here's the part worth sitting with before we go any further. This current has never once in the entire span of modern record-keeping reshaped the country the same way twice. Every transition carries the same basic mechanics, but the specific regions that end up flooded, the specific regions that end up parched, and the specific month an out-of-season disaster arrives, all of that depends on details in the ocean that are still actively forming right now, this season, which is exactly why understanding the mechanism matters more than trying to guess the outcome in advance. Let's start with exactly what's happening, because the small details here matter a lot more than you might think. And it's worth knowing that fishermen off the coast of Peru noticed this pattern centuries before any scientists put a name to it. Every few years, right around Christmas, they'd watch the cold water their catch depended on turn warm, and the fish they relied on would vanish from their usual grounds. They called the warm current El Niño, the little boy, a reference to the Christ child because of when it tended to arrive. It took modern oceanography until the 20th century to figure out that what those fishermen were describing wasn't a local curiosity off their own coastline. It was the visible edge of a shift big enough to eventually touch nearly every country that borders the Pacific, including this one. Out in the middle of the Pacific Ocean, along a stretch of water roughly the size of the continental United States, the surface temperature does something most people never think about. Most of the time, it sits in a kind of quiet, in-between state, but every 2 to 7 years, without any fixed schedule, that patch of ocean either warms up significantly above normal, a phase called El Niño, or cools down significantly below normal, a phase called La Niña. Either way, that shift changes how heat moves from the ocean into the atmosphere above it, and that change ripples outward across the entire planet within a matter of months. For the last several years, large parts of the country have been living under a La Niña dominant pattern or a neutral phase caught in between. That pattern has a signature. It tends to push the jet stream north, which tends to leave the southern United States drier than normal, feeds persistent drought across the southwest and southern plains, and tends to load the dice toward more active hurricane seasons in the Atlantic because La Niña removes a wind pattern that would otherwise tear budding hurricanes apart before they can strengthen. You can see the fingerprints of that signature on the Colorado River system right now. Reservoirs like Lake Mead and Lake Powell have spent years fluctuating near historically low levels, drawn down by a combination of demand across 7 states and a La Niña-leaning pattern that simply hasn't delivered the snowpack the river depends on. Millions of people across Arizona, Nevada, and Southern California get their water from that single system, which means a shift in an ocean current thousands of miles away has been quietly setting the water bill for one of the fastest-growing regions in the country. This particular stretch has been unusual even by La Niña standards, what climate scientists sometimes call a triple dip, where the pattern weakens toward neutral, looks ready to flip, and then strengthens back into La Niña again, sometimes 3 winters in a row. It's happened only a handful of times since reliable ocean records began, and each time the eventual transition out of it has arrived with more built-up energy behind it than a single-year La Niña ever carries. Now that pattern is breaking down. Ocean temperatures in the key monitoring zone have been trending toward the threshold that officially defines a transition, and when NOAA's Climate Prediction Center starts using the word transition in their monthly outlooks, meteorologists pay very close attention because a transition year is historically the most disruptive kind of year there is, more disruptive in terms of nationwide impact than a year that's locked firmly into either extreme. The way scientists actually track this isn't guesswork. There's a stretch of open ocean along the equator, officially labeled the Niño 3.4 region, monitored around the clock by a network of moored buoys that measure sea surface temperature down to a fraction of a degree, and have done so continuously since the late 1980s. When the average temperature across that region sits more than half a degree Celsius above the long-term normal for 5 overlapping 3-month periods in a row, that's the official threshold for El Niño. Below half a degree, sustained the same way, that's La Niña. It sounds almost too simple for something that reroutes weather across an entire hemisphere, but that's exactly the point. A change measured in fractions of a degree, in a patch of ocean most people will never sail across, is the trigger for a chain reaction that eventually shows up as your neighbor's flooded basement or your cousin's canceled ski trip. Forecasting this transition is a different job today than it was in 1982, and that difference matters. Back then, scientists were reconstructing an event that had already devastated 3 continents before anyone fully understood what caused it. Today, dozens of independent computer models, run by NOAA, by universities, by international weather agencies, each simulate how the ocean and atmosphere are likely to evolve over the coming months, and forecasters overlay all of those simulations on a single chart that, because of how it looks, everyone in the field just calls the spaghetti plot. When most of those individual model lines cluster tightly together, heading the same direction, confidence in the forecast is high. When they fan out in a dozen different directions, confidence is low, and honest forecasters say so plainly instead of picking the most dramatic line and running with it. That's the entire difference between a channel that respects you and one that doesn't, whether it shows you the spread or just the scariest strand of spaghetti. And it isn't only the temperature. Underneath the surface, along the equator, there's a wind pattern called the trade winds, blowing steadily east to west, that normally piles up warm water on the western side of the Pacific, near Indonesia and the Philippines, while cooler water wells up from the deep near South America. During a transition toward El Niño, those trade winds weaken, sometimes even reverse direction for a stretch, and that pile of warm water sloshes back eastward like tilting a bathtub and watching the water rush to the other end. That sloshing warm water is what eventually reaches the Niño 3.4 region and crosses the threshold. It's a slow-motion process, usually taking months to fully develop, which is exactly why scientists can see it coming well before its full effects reach American soil, and exactly why a video like this one exists now, while the shift is still forming instead of after it's already reshaped a season. Here's another way to think about it. A stable La Niña, or a stable El Niño, is like a room with the thermostat set and left alone, predictable, even if the temperature itself isn't comfortable. A transition year is like someone standing at that thermostat turning the dial back and forth, testing it while the room tries to catch up. The atmosphere doesn't like whiplash any more than we do. When it gets it, the result is a season of extremes rather than a season of consistency. Record heat next to record cold, drought next to flood, sometimes separated by only a few hundred miles in a few weeks. So here's the question worth sitting with before we go any further. If a shift like this has already happened multiple times in living memory, why does it keep catching entire regions off guard? The honest answer is that the ocean part of the story gets tracked closely by specialists, but the land part, the part that actually floods a neighborhood or dries out a reservoir, rarely gets connected back to its cause in the public conversation. People remember the flood, people remember the drought. Almost nobody remembers the ocean current that quietly set both of them in motion months earlier. This isn't a new phenomenon, it's happened before, and looking at what happened those times tells us almost everything we need to know about what could be coming. There's also a bigger historical pattern worth understanding here, because this isn't the first time the ocean has flipped mid-decade and rewritten the forecast for tens of millions of people who had no idea anything in the Pacific had changed at all. To understand how big this kind of shift can get, we have to leave the ocean completely and look at what happens on land when the jet stream reroutes. The jet stream is a river of fast-moving air, 5 to 9 miles above the surface, and it acts almost like a fence separating cold northern air from warm southern air. Where that fence sits determines almost everything about a season's weather. When El Niño strengthens, the jet stream tends to dip further south and split into 2 branches, a northern one and a southern one, and that southern branch acts like a fire hose, aiming storm after storm at California and the Gulf Coast, while the northern tier of the country, from Washington state to the Great Lakes, often ends up warmer and drier than normal. Think of it like a garden hose you're using to water a long row of plants. Move the hose 2 feet to the left, and the plants on the right go thirsty while the ones on the left start to drown. The jet stream is that hose, except instead of watering a garden, it's deciding whether an entire region gets a normal winter, a historic drought, or a season of flooding that overwhelms infrastructure built for an entirely different pattern. There's a second mechanism working alongside the jet stream that most forecasts never mention by name, and it might be the more important one. Scientists call it the Walker circulation, a giant, slow-rotating loop of air that normally rises over the warm western Pacific, travels east at high altitude, sinks over the eastern Pacific and South America, then crawls back west along the surface as the trade winds. During a transition, that entire loop shifts thousands of miles east, dragging the rising, storm-generating branch of the circulation with it. Picture a Ferris wheel the size of an ocean basin, and someone reaches in and slides the whole structure sideways. Everywhere the rising air used to be, it's suddenly gone, and dry, sinking air takes its place instead. Everywhere the sinking air used to dominate, rising, storm-fueled air moves in. That single sideways slide of the Walker circulation is the underlying engine behind almost every regional flip we're about to talk about. It's the reason a shift in one patch of open ocean can simultaneously drown one coastline and starve another of rain it was counting on. There's one more piece of machinery worth understanding because it's the part that actually shows up on your local news as atmospheric river, a term that's become common in the last decade but describes something that's always existed. When that southern branch of the jet stream taps into the warm, moisture-rich air near Hawaii, it can form a narrow, fast-moving corridor of water vapor thousands of miles long, sometimes carrying more water than the Mississippi River carries at its mouth, aimed directly at the California coast. Meteorologists call the strongest of these atmospheric river families when 3 or 4 arrive back-to-back within a couple of weeks, and El Niño years are historically when families like this become far more likely. Because the same southern jet stream branch that steers storms toward California in general becomes the exact conveyor belt that lines these rivers up one after another instead of spacing them months apart. A single atmospheric river on its own is often exactly what a drought-stressed reservoir needs, welcome, even beneficial. The danger isn't any one of them. It's the 4th one or the 5th arriving on top of ground that's already saturated and hillsides that have already lost their grip when the same storm that would have been a blessing in October becomes a disaster in January. It also isn't a light switch. Real transitions build in stages, and meteorologists watch each one like rungs on a ladder. First the trade winds weakening, then the subsurface warm water sloshing east, then the surface temperature crossing threshold, then finally the atmosphere itself responding by shifting the jet stream and the Walker circulation into their new positions. That last step, the atmosphere actually catching up to what the ocean has already done, is usually the slowest part, and it's also the part happening right now across meteorological models, which is exactly why the full on-the-ground impacts of this shift are still ahead of us, not already behind us. The winter of 1997 into 1998 is the case study meteorologists still reference today because that El Niño event was one of the strongest ever measured, and the fingerprints it left on the country were almost too clean to be believed. California absorbed storm after storm that winter, with rainfall totals in some areas more than double the historical average, triggering mudslides that swept homes off hillsides in Southern California. At the very same time, the Northeast and Upper Midwest experienced one of the mildest winters on record, so mild that some ski resorts in New England closed for lack of snow, while families in Malibu were sandbagging their front doors. Same country, same season. 2 completely different disasters, both caused by the exact same shift in the exact same current thousands of miles away in the Pacific. I need to pause here and be completely honest with you because this is where a lot of channels lose the plot. I'm not telling you that this transition will produce another 1997. I'm not telling you exactly which state gets the flooding and which gets the drought this time. Anyone claiming they can pin the precise regional outcome of an ENSO transition down to the month, this many months out, is not being honest with you. What climate scientists can tell you, with real confidence, is that transition years carry a documented history of producing sharper regional extremes than stable years, and that history is exactly why this shift is worth understanding now, not after the first headline. There's a real difference between forecasting weather and forecasting climate risk, and it's a difference worth holding on to for the rest of this video. Nobody can tell you if it will rain in Dallas on a specific afternoon 4 months from now. But climate scientists absolutely can tell you that a transitioning ENSO pattern measurably shifts the odds. The same way a casino can't tell you which specific hand you'll win, but can tell you with total confidence what the odds look like across 1,000 hands. This video is about the odds shifting, not about a single guaranteed outcome. If you want to actually understand how those odds play out on the ground, hit that subscribe button now, because what happened in Texas the last time this exact kind of transition unfolded is the part that still keeps meteorologists up at night, and it's exactly where we're headed next. Go back even further, to the winter of 1982 into 1983, and you find the event that first forced meteorologists to take this ocean-to-weather connection seriously at all. That El Niño arrived almost without warning by the standards of the time, because the monitoring network we rely on today simply didn't exist yet. Scientists were essentially caught reconstructing the disaster after the fact instead of watching it build in advance. Along the coast of Peru and Ecuador, fisheries that entire economies depended on collapsed within weeks, as the usual cold, nutrient-rich water that fish and the birds that feed on them rely on was replaced by a warm, nutrient-poor layer that simply couldn't support the food chain. On the other side of the Pacific, the same event triggered one of the worst droughts Australia had seen in decades, fueling wildfires that burned for months. And on American soil, California absorbed a series of storms so severe that a fishing pier in Santa Cruz that had stood for generations was torn apart by the waves in a single night, while the Ohio and Mississippi River valleys saw flooding that displaced tens of thousands of people who had never lived through anything like it. 3 continents. One shift, thousands of miles away in the Pacific, cashing in as 3 completely different disasters almost simultaneously. That same warm water disruption reaches American fisheries too, not just South American ones. Along the Pacific Northwest coast, the cold, nutrient-rich water that salmon runs depend on for food gets replaced during a strong El Niño by a warmer, emptier layer scientists sometimes call the blob, when it persists for extended stretches. And salmon populations that fishing towns from Oregon to Alaska depend on for their livelihoods can drop sharply within a single season, with effects on quotas and local economies that last for several years afterward, long after the ocean itself has moved back toward normal. The 2015 into 2016 transition is another data point worth knowing because it shows the flip side of the pattern, what happens when the shift runs the other direction. That El Niño, one of the three strongest on record, ended a punishing multi-year drought across California almost overnight, refilling reservoirs that had dropped to historic lows, but it also fed a stretch of tornado outbreaks across the South in the dead of winter, a season when tornadoes are supposed to be rare, not headline news. Rowlett, Texas, was hit by an EF4 tornado on December 26th, during what should have been one of the quietest weeks of the year for severe weather. No rumble that built for hours, no days of warning on cable news, no seasonal expectation that prepared anyone for it, just a transition year doing what transition years do, breaking the rules that the calendar usually protects us with. The most recent strong transition in the winter of 2023 into 2024 gave an entire generation of Californians a live demonstration of what an atmospheric river family can do once a strengthening El Niño lines the storms up back to back. Over a single stretch of weeks, Los Angeles received more rainfall than the city had recorded in years, turning hillside neighborhoods into evacuation zones and burying stretches of the Pacific Coast Highway under mudslides that closed the road for days. San Diego saw flash flooding severe enough to strand cars on freeway overpasses in a city where residents genuinely struggle to remember the last time storm drains simply couldn't keep up. At the same time, states in the northern tier were logging some of the mildest, driest winters in their own records, with several ski areas in the northern Rockies opening weeks late for lack of natural snow. It was the same signature as 1997 and 1982 before it: one ocean shift, one country, two entirely different disasters unfolding at the same time under the same sky. Here's the part that gives me chills. The people who lived through that December outbreak in North Texas describe the same thing survivors of out-of-season disasters almost always describe: the sense that the danger wasn't supposed to be possible in that month, in that place, at that time of year. That's the signature of a transition year. It doesn't wait for the season everyone's braced for. It borrows danger from the wrong month and delivers it early, or late, or somewhere the historical odds said it shouldn't be at all. So let's bring this back to right now and to you, because a transition of this kind doesn't stay an abstract ocean story for long. If the shift plays out the way climate scientists are watching for, the impacts sort into a few distinct zones across the country, and where you live likely puts you in one of them. Across the Southwest and the Southern Plains, Arizona, New Mexico, West Texas, and Oklahoma, a strengthening pattern typically means a wetter stretch ahead after years of entrenched drought, which sounds like good news until you remember what wildfire scientists call the grass fire cycle. Extra rain in a drought-stressed landscape doesn't just refill reservoirs. It grows an enormous amount of fast-drying grass and brush, and when the pattern swings back toward dry conditions the following season, that overgrown vegetation becomes exactly the fuel load that turns an ordinary spark into a fire that outruns containment lines. Some of the most destructive wildfire seasons in California's history followed directly on the heels of a wet transition year, not a dry one, oh. The grass that exploded across hillsides after a historically wet El Niño winter was exactly the fuel load that, once the pattern swung back toward dry conditions, helped drive some of the costliest wildfire seasons the state has ever recorded, with damages running into the tens of billions of dollars once homes, infrastructure, and firefighting costs were all added up. For farmers and ranchers across this corridor, the wetter stretch also means watching pasture and rangeland rebound faster than usual, which sounds like relief after a drought, but often tempts operations into restocking herds at a pace the land can't sustain once the pattern reverses again a year or two later. Across the Gulf Coast and the southeast, a fire hose-style storm track means an elevated risk of heavier, more frequent rain events layered on top of coastal areas that are already dealing with rising base flood levels, which means the same rainfall total that used to be a nuisance can now be the difference between a wet parking lot and a flooded emergency room. Cities like Houston, New Orleans, and Tampa, all of them built on flat, low-lying ground with drainage systems designed decades ago for a different rainfall climate, sit at the center of this risk, and insurers in these markets have already been adjusting flood zone maps and premiums in anticipation of exactly this kind of pattern, whether or not most homeowners have noticed the paperwork changing. Across the northern tier, the Pacific Northwest, the Northern Plains, and the Upper Midwest, the historical signature leans warmer and drier than normal, which is a mixed blessing at best. Lower heating costs in a mild winter, but a head start on drought stress heading into the following growing season, and a snowpack that mountain communities and downstream farmers depend on for water through the summer. In places like Seattle, Minneapolis, and Fargo, a mild winter often means less road salt spent and fewer burst pipes in any single season, but it also means the reservoirs and river systems that entire agricultural regions rely on come summer are starting from a smaller cushion than usual, and a single dry follow-up season can turn that cushion into a real shortage. And in the transition zone in between, the Ohio Valley, the Mid-Atlantic, and parts of the Southeast, the risk is the one that catches people most off guard because it's the risk of pattern whiplash within a single season. A mild stretch that lulls a region into a false sense of an easy winter, followed by a sudden reversal that brings an outbreak of severe cold, ice, or even out-of-season severe weather, the same way North Texas got its December tornado in a year the calendar said should have been quiet. Cities like Nashville, Louisville, and Richmond sit squarely in this zone, and it's worth remembering that infrastructure here is often built for the region's normal range, not for the sharper swings a transition year can produce, which is exactly why an ice storm or an out-of-season severe outbreak tends to do disproportionate damage here compared to regions that build for extremes as a matter of course. This same whiplash risk extends into the power grid itself. Regions that experience a sudden sharp cold snap after weeks of mild weather see natural gas demand spike far faster than utilities plan for in a normal year. And it's exactly that kind of rapid swing, not a gradual, well-forecast cold season, that has strained grids in Texas and the Mid-South in past transition winters, leading to rolling blackouts at the worst possible moment. I'm not saying stockpile a bunker. I'm not saying cancel your plans for the season. What I am saying is this. A transition year rewards the households and the towns that build in flexibility now, while the pattern is still forming instead of reacting to whichever extreme shows up first. So here's what actually helps, and none of it requires predicting the future with more precision than the atmosphere itself allows. First, if you live in a drought-recovering region in the Southwest, this is the season to clear defensible space around your home. Even modest brush clearing, 30 feet out from the structure, measurably changes outcomes when a wet year's extra vegetation dries out and fire risk returns the following season. Second, if you're along the Gulf Coast or Southeast, check your flood insurance now, not during hurricane season. Many policies have a 30-day waiting period before coverage kicks in, which means waiting until a storm is already in the forecast is often too late, and it's worth confirming your policy covers the updated flood zone designation for your address, not the one it carried a decade ago. Third, if you're in the northern tier watching for a mild winter, don't let a warm stretch fool you into skipping normal cold weather prep, pipe insulation, an emergency kit with a few days of water and non-perishable food, a plan for checking on older relatives, because transition years are exactly the years that produce the sharpest late-season reversals, often after weeks of mild weather have already lowered everyone's guard. Fourth, if you're in the Ohio Valley or Mid-Atlantic transition zone, this is worth a conversation with anyone in your household who assumes it's usually mild here. A single out-of-season ice storm or severe outbreak can knock out power for days in a region that doesn't budget for it the way harder-hit regions do. Fifth, if you're anywhere in a region prone to grid strain during sudden cold snaps, this is a good season to have a backup plan for a multi-day power outage that doesn't depend on the outage being forecast a week in advance, a battery-powered radio, a way to charge a phone without the wall, and a plan for keeping any medications that require refrigeration safe. And sixth, wherever you are, this is the season to actually know your county's severe weather alert system before the pattern breaks, not during it. Most areas have a free app that pushes tornado, flood, and severe thunderstorm warnings straight to your phone, and out-of-season events like a December tornado outbreak catch people off guard specifically because they arrive outside the window most people are mentally prepared for. There's an economic layer to all of this that rarely makes it into the forecast graphic but shapes the season just as much. Commodity traders watch ENSO transitions closely because a wetter southwest and a drier northern tier can shift corn and soybean yield expectations enough to move futures prices before a single combine has entered a field. The Mississippi River, which barges a huge share of the nation's grain exports downstream to port, runs low enough during entrenched La Niña droughts that shipping companies have had to lighten barge loads or halt traffic in low water stretches entirely. A transition that eases that drought in the river's northern watershed can just as easily ease that bottleneck, even as it creates new problems somewhere else. And insurers, who price risk for a living, have already been quietly adjusting premiums in flood-prone Gulf Coast markets and fire-prone western ones in anticipation of exactly the kind of regional swing a transition year produces, which means, in a very real sense, the ocean's mood thousands of miles away is already showing up in paperwork. Most households haven't opened yet. None of this is about fear. It's about respect. Respect for a pattern that has historically reshaped more of this country in a single season than most people ever give it credit for. If you made it all the way here, you already understand something most people never learn until their own region shows up in a headline, that the weather over your house isn't a local story. It's the last domino in a chain that starts with ocean temperatures thousands of miles away, and by the time you can see it on a forecast map, the pattern behind it has already been building for months. You know the difference between a stable pattern and a transition year now. You know why the same shift that floods one coastline can leave another one begging for rain. And you know that the real warning sign isn't a single scary forecast. It's the slow, month-long process happening quietly in a stretch of ocean most of us will never see. That's the difference between watching the weather and actually understanding it, and it's a difference that will keep paying off long after this particular transition has finished playing out. Before you go, if channels like this one matter to you, the ones that explain the real mechanics instead of just chasing the scary headline, and hit that subscribe button, because the next part of this story, the part where scientists confirm exactly how strong this transition is getting, is the part that determines just how sharp these regional extremes end up being. If you're in one of the zones we talked about today, drop your region in the comments. I read every single one. And I want to know how this pattern has actually played out where you live in past transition years, not just what the historical data says from 3,000 miles away. And if this kind of shift is new to you, one question before you leave. When a whole season feels unusually calm, do you trust the calm or do you trust the pattern building underneath it? Let me know down below. Stay safe out there. I'll see you in the next one.